generator topics. Last class we stopped at this point at the power and torque characteristics of synchronous machine. So we will derive the equation of power. طبعا you know شباب the power relation, the apparent power S equals V multiplied by I conjugate. This is for per phase power. So if we would like to calculate this according to the synchronous machine, we have the current which can be obtained from the equation of volt. Okay, you know EF equals V terminal plus JIAXS plus IARA. So if we get the current from the synchronous machine equation and substitute here in this relation, you will find that the relation S equals V terminal EF over ZS at angle theta S minus delta, where theta S is the angle of the impedance, the power factor angle, minus V terminal square over ZS at angle theta S. So this is the relation of apparent power. The active power is nothing but the real power, which is the real part of this complex number. So we can say that the active power equal V terminal EF over ZS cosine angle theta S minus delta minus V terminal square over ZS cosine the angle here, which is theta S. And for the reactive power, it will be the imaginary part. So it's the same except replacing a cosine by sine. So this is the active power and this is the reactive power. Now, شباب, for synchronous generators, if we neglect the armature resistance due to the high current, the resistance will be very, very small due to the high cross-section area of windings. So we can neglect the resistance RA, and in this case, we can get the angle if we neglect the value of real part. So the angle of theta will be 90 degrees. So in this case, شباب, we can say that طبعا theta S is the angle of the impedance شباب. Theta S is the angle of the internal impedance of the synchronous generator, not the power factor, sorry. Theta S is the angle of the impedance, which is RA plus JXS. Okay, if we neglect the resistance RA, so the impedance will be JXS and theta will be 90 degrees in this case. So if we substitute here in these two equations, شباب, we will find that power equal, طبعا if we get it here for three phase now, okay, 3 V terminal EF over XS sine delta, which is B max sine delta. So this is the value of maximum power, 3 V terminal phase EF phase over XS. The same is for the reactive power. By applying ZS equal XS and theta equal 90, we will get the relation 3 V terminal EF over XS cosine delta minus 3 V terminal square over XS. So this is the relation of reactive power. If we would like to calculate the torque, torque equals power over speed. So power of three phase over the synchronous speed. So we can say now 3 V terminal EF over XS omega multiplied by sine delta, or we can say also T maximum sine delta. So we have now, شباب, two or three relations. These are the most used. We have first relation here of power, this one, this relation. We have the torque relation and the reactive power relation. Yani no need to drive the equations, we just need the final forms. And these are the relations what we are going to use all of time. And we are not going to use the relations where R is exists, because in most of synchronous machines we neglected the armature resistance. Type. In this case, شباب, if we would like to represent the shape of the waveform of power or torque versus delta, we will find that this is the angle delta, and it's sinusoidal wave. So this is the curve of power, and here, if we divide by omega, we will have the other curve of torque like that. Now, we can see that the maximum torque is appearing at 90 degrees, and the same is also for the power. The maximum power is attained at delta equal 90 degrees. So we can now, Shabab, give a name to this point, this operating point, as the maximum power or maximum torque or pull-out power and pull-out torque. Also, there is another name called steady state stability limits. Why it's called the steady state stability limit? This is what we are going to discuss now. Any question here, Shabab, regarding the relations?
Yes, I have a question. Sorry, Doctor.
Fadal.
Why we neglect the armature resistance in the synchronous machine?
Again, synchronous machine, we said it's most likely work as a generator. And generator is very high power machines. Generators in power plants are very high power machines. Like for high power machine, what do you expect the current? Is it going to be small or high current? What do you think?
High current.
High current.
It should be high current. So what about the conductors? The machine conductors itself, the windings. In order to have or to carry high current, you need high cross-section area, large diameter. Is it right? And for large diameter, you know the relation of resistance. Resistance equals rho multiplied by L over the cross-section area of the wire. So for high cross-section area, we expect to have very small resistance. So we can neglect the armature resistance compared to the synchronous reactance. Okay, so R can be neglected compared to XS. Okay, and you will see this in the problems. Yani if we have a look to the problem of the last class, which we skipped here, it was given the armature resistance is 0.07 ohms. Okay, when we obtain the armature reactance, the value was 19.6. This is the total impedance, 19.6. Okay, when you substitute, you will get, sorry, this is the base X here, okay, 21 ohms, okay, 21.21. This is the impedance, and when you calculate the reactance, it will be 21.2. So, yani, comparing R with X, you will find R very, very small. Okay, and it will be trivial in the calculation. So we can neglect the armature resistance from calculation just to simplify the equations. Fine. Any other question, Shabab, here in this part?
This is for just generators, but in motors maybe we'll have other issue.
For large synchronous machines.
Okay.
Large in general, whatever about a motor or generator. Okay. Now regarding the stability, and we said the maximum power point is called also steady state stability limit. Now let's discuss about the dynamics of the synchronous machine and the definition of stability. Generally, Shabab, the definition of stability, power system stability is the property of the system that ensures it will remain in synchronism and maintain the state of equilibrium following a disturbance or disturbing force, which means if we are operating at a certain point, assume we are working at this point here. If I got any disturbance to change the operating point, for instance, a disturbance make the angle increase, the value of delta to be increased. If the power system itself by their own return it back to operate at the same operating point again after this disturbance, we can call that this system is stable. And if the system could not return to the same operating point and deviate to other values, in this case we can call the system is unstable. Let me give you small example. If you have a cup like that and you have a small ball inside, and if you by your hand press here to move this small ball, okay, it will oscillate a bit and it will stay in the cup. Is it right or not?
Yes.
مظبوط كده يا شباب. So if we applied a disturbance here, due to the situation of the cup with the ball will return back to the same point again. So we can say now this is an example for a stable system. Now, if we have a cup like that, and the ball is here on the top, and if you make any disturbance, just touch this ball, what will happen?
It will fall. It will fall off.
It will fall.
Exactly.
Run away.
Is it going to return back again in this case?
No.
So we can call it that this an example for unstable. Okay, شباب. So this is the meaning or the just simplification for the meaning of stability for any system. Right. If we made a control system that can return back the ball to the top point here again, we can say that we can operate at unstable regions, but just if we made closed loop control. Okay. However, for stable regions, we can operate without closed loop control because it's already will stay at the same place. يعني what I mean here يا شباب, if you make a disturbance to the ball here, however, you add some barriers here like that to avoid the dropping the ball away. So in this case, you have external thing that try to keep the operating point at the same place. In this case, the system is unstable. However, you added a control, external control, in order to keep the system operating at its place. Okay. However, if there is no barriers here for this ball, it will be a dropped. So the system without closed loop control here is unstable. Okay. Stability has two categories. What are the two categories we care about here? The two categories are the steady state stability, which means the machine is already working at steady state, and we have some changes due to, for instance, load change, but gradually increase in load, not suddenly increase. Okay, so we can consider this as steady state stability. Steady state stability. However, we have also another category, which is transient stability. Transient stability is considered at certain disturbances, like sudden change in load, like outage of line, open circuit, for instance, like fault, short circuit, for instance. Okay, so these are considered as transient stability issues. Okay, شباب. So we have steady state stability and we have transient stability. For that, we call the operating point here steady state stability limit, which means if you move the machine operation after delta equal 90 degrees, you will go to the unstable region at steady state. Okay, and it's not preferred to do that. So the maximum or the steady state stability limit is the delta equals 90 degrees. طيب. طبعا it's very important شباب to recognize the different names because it may be in an example or problem you will find the just hint about the this point by any of these names, and we will not say delta equal 90 degrees. And you cannot solve the problem if you did not substitute delta equal 90. So you have to recognize the different names of the operating points. طيب.
Doctor,
تفضل.
I didn't get the transient stability.
Okay, transient means something happened in very short time. Transient, all of time يا شباب, transient means changes at very small time. يعني for instance, if we change the load gradually during time, for instance, we need to increase the output of the generator by 2 megavolt ampere during 1 minute or 2 minutes. There is no problem in that. We will start increasing the prime mover power. If we have, for instance, steam turbine, we are going to increase the steam by opening the valves, okay, in order to increase the output power. This is called gradually increase, okay. However, if the power increased immediately due to any problem, like for instance, you have 2 power plants operating certain region, and one of them is blacked out, turned off due to any problem. In this case, you will have a very huge load on the operating power plant. This is called suddenly increase in load or suddenly change in load. This is considered transient. Why transient? Because it happened in a very small time, in several milliseconds. So this is called transient stability, and it needs special treatment compared to the steady state stability. Okay, so this is the difference between transient and steady state. Transient means something happened very fast during very small period of time. Okay.
Yes, clear. Thank you.
Yeah. And by the way, شباب, the equivalent circuit of the machine itself will be different at transient conditions. Transient conditions is different a bit. يعني طبعا we are not going to discuss the transient conditions here in our course. Okay. يعني it's the level of transient analysis يعني is higher a bit to undergrad. However, we care only about the steady state analysis only. طيب. Let's have an example يا شباب for the stability here by studying or analyzing the stability of synchronous machine. طبعا we have now يا شباب the relation of power. Assume first we have single machine infinite bus. Single machine infinite bus. Like that. We have generator, we have transformer, and part of transmission line, and this is considered as the infinite bus. So we can call this as single machine infinite bus. And the equivalent circuit of this single machine infinite bus will be like that. We have here generated voltage at angle delta G. We have the summation of reactances here due to generator, due to transformer, and due to transmission line. So this is the total reactance. And finally, we have terminal voltage here, ES, or sending at angle delta S. Now, if we would like to analyze the stability of this part, we have to refer to the dynamic equation, شباب. Dynamic equation, which is torque mechanical minus torque electrical equals J d omega by dt. We'll discuss it in details soon, inshallah, in terms of something called swing equation. المهم, now in order to study the stability for the operating curve here, let's see together the characteristic at some points, for instance, at point number A. As you can see, Shabab, this is now the electric power change with delta, and we have a certain operating point by the intersection with PM at point A and point C. Let's see together at point A and apply here the to the equation. If we have a disturbance, if at point A we have a disturbance that increases the value of delta. So increasing the value of delta means B electric will be greater than B mechanical. So what will happen here, ya shabab, when we substitute in the equation here? If we have B electric greater than B mechanical, so this means T electric is greater than T mechanical. So what will happen to the speed of the machine?
Decrease.
It will decelerate. Is it right?
Yes.
The machine will decelerate. And if the machine decelerates, what will happen to the power angle now?
Decrease.
It will decrease again. It will decrease. So if the power angle decreases, Shabab, what will happen? Delta will be decreased, so it will return back again to the same operating point. Is it clear? So after the increase, the dynamics of the machine itself returns the operating point to the same point again. So after disturbance increases the value of delta at point A, when we check the dynamic equation here, we could find that the machine will decelerate, which will make the value of delta to return back again to the same point. So for that, Shabab, we call this point is stable. But let's apply the same here at point C and check what will happen if we have small increase in delta. Apply the same here in the equation. You will find that increasing delta here will make power electrical smaller than power mechanical, which means power electrical is smaller than power mechanical, so d omega by dt will increase, which will accelerate the machine. Accelerating the machine will increase the power angle, which means the power angle will go more in this direction. So this point is called unstable point. Okay, Shabab? So this is the analysis from the curve and dynamic equation, how we can define the stability of the machine. طبعا for that يا شباب, you will find that يعني this is valid, the unstable is valid for all parts from point P up till this point, and the stable region is from 0 to delta equal 90. So all of this is considered as a stable region. So we can now say that this is stable region for the synchronous machine. Any question, Shabab?
Yeah, the last point at point C, it's not clear for me.
At point C, again, if you if you assume a disturbance increasing delta, so assume delta became here now at that point. Here, which value is greater, B electric or B mechanical?
B mechanical.
Exactly. If you substitute here in the equation, you will find that B mechanical or T mechanical is greater than T electrical. This is going to increase the machine speed or accelerate the speed, accelerate the machine. Tamam?
Increase or decrease?
Increase. If you have this side
it will
is
increase
positive,
to make it stable.
Exactly. If you have this side is positive, this means d omega by dt is positive. D omega by dt is positive means the machine speed is increasing. If you have T mechanical equal T electrical, so this side is 0, which means d omega by dt is 0. This means the machine is working at constant speed. There is no acceleration or deceleration. Okay? which means it's working at equilibrium. تمام? So if we have this side is positive, this means there is acceleration in the machine. And acceleration in the machines means the power angle will be increased. So this means at that point, if the delta increase to that point, it will increase more. So it will not return back again to the same operating point. For that, we call this is an unstable point. Okay? Is it clear now?
Doctor,
Yeah, now it's clear because in our notes maybe some mistake there.
Yeah, sorry. Yeah. I updated. There was typo here in this two sentences شباب. The last two sentences. كويس إن أنت فكرتني. يعني I updated the slides here. I will update it for you إن شاء الله today on Blackboard. Okay? يعني the text there was some typo, so I changed the two expressions here شباب.
Doctor, in the
Yes,
case if delta decreases, we will have a different situation.
The same. It will be the same. Apply again here if the delta is going to decrease. We said here delta increase. Decrease the value of delta here. When you decrease the value of delta, this is going to make B electric less than B mechanical, which means the machine has to be accelerated and increase the value of delta. So it will increase again to reach to point A. Okay?
I mean, if we in point A,
أيوة.
if we decrease the delta, the
Yes.
point will be unstable, right?
لا. It will be stable as well. Again, I give you an example here. If delta decreased here, what will happen? Huh? What is the value of B electric compared to B mechanical now?
The B mechanical will be higher.
Exactly. So this means the machine will accelerate.
Okay.
So it will return again to the same operating point. Okay?
Yes.
Yeah. For that, يا شباب, all of region, all of the curve from the origin point to point B, okay, will be stable, and from point B to the value at delta equal 180 is unstable. Okay. Any other
So doctor,
تفضل.
so if we have to increase the power angle, then the system's going to be unstable, like in general.
Increasing power angle over 90 degrees. Yes.
Over 90 degrees, yeah.
Yes. It is unstable. Yes. Okay. طيب.
يا دكتور
تفضل.
هو الباور انجل it can be controlled.
We have to control the power angle according to the definition now يا شباب. يعني let me give you an example before discussing how to increase the stability. يعني assume this is the stator. And this is the rotor, okay? And we have here, this is the machine X, okay? And we have another line like that. Neglect this line firstly. This is the X of the machine. What is the meaning of X? Now, يا شباب, in order to imagine any rotation of the machine, we have to make a reference. So assume that this is our reference. So this is here our reference, which means the machine flux, stator, flux, and rotor are moving at the same X. Assume this pole is N here, and the other pole here is S. And here, due to the flux of the stator, we have bool S, and we have some flux lines here from N to S. Okay. If you added a load to the machine, which will make the machine to decelerate, sorry, not the machine to decelerate, the rotor. What's happened? Oh. It's a collapse. Sorry, شباب. طيب خير. And let's do it in Word. You can see the Word screen يا شباب?
Yes.
Yes, doctor.
Yes.
طيب. Again, if we have a circle of the stator and another circle of the rotor here inside, like that, and we have this is the axis of the machine, تمام, and this is the poles here. We have here a pole N, for instance. This pole is moving يا شباب طبعا. The stator poles are moving due to the air rotating flux. And here we have pole S. So there are some flux lines moving in this direction. Now, if a load is applied to the machine, load is applied to our rotor, so we expect to have a small shift between stator and rotor. So assume that the rotor X will be delayed like that. So this means that the pole S here will be shifted to be in that point, and the flux lines will be stretched like that. تمام يا شباب? Do you got it?
Yes.
This is due to the load increase. Actually, this is the angle delta. If now delta increase يا شباب to reach to 90 degrees, but 90 degrees electrically, okay, which will be different according to the number of poles of the machine, okay, you will find that the machine flux lines will be stretched too much. And if you increase more, the flux lines itself will be cut. And this is going to make something called desynchronization or unsynchronizing the A, or loss of synchronism of the machine, okay, due to the A increase in loads. تمام. For that يا شباب, we have to keep our machine stable. How to keep our machine stable? Avoid reaching to delta equal 90. Now, if we have the relation now, which is power equal EF V terminal over XS sine delta. And you know sine delta from 0 to 90 degrees is linear, which means delta is proportional to sine delta. So V terminal is constant, XS is constant. In order to achieve certain range for delta, what you can do is to control the excitation voltage. Is it right, شباب?
Yes.
Yes.
Is there any other way, شباب, now? Only we can control X by decreasing X. However, decreasing X needs extra actions. We will see now how we can do that. Right, let's see again. So we can control delta by increasing the flux. So here we can say that methods to improve the stability of the machine is to increase the excitation of the generator. Okay. Another way is to reduce the reactance. But how we can reduce the reactance? Let's see together يا شباب if we have, this is our generator, and we have here 2 transmission lines instead of 1. If we have 1 transmission line, this is going to have high value of X. However, if we add transmission lines in parallel, this is going to decrease the value of reactance. So decreasing or reducing the value of reactance as well, improving the stability. طبعا in terms of stability, it's clear from numbers, because 2 parallel reactances will be lower than the A, will be 1/2 of, يعني if they are equal in reactance, it will be 1/2 of them, okay? And in terms of reliability as well, which means if we lost one of the lines, it means the other line can carry the power to the load. So it's improve also reliability of the system. تمام يا شباب? Is it clear? For instance, here, in order to calculate the power or maximum power that can be transferred, if this is the sending end and this is the receiving end VR, we can say now the power or maximum power equals EF of the generator, VR over XT, where XT is the total reactance, synchronous generator reactance, plus 1/2 of the 2 reactances here if they are equal, or if we have many from line 1 to line N, it will be X over N. Okay, شباب? So this is the way to improve the stability by decreasing the reactance. تفضل.
Doctor, what's the limit for us when we add, like, parallel transmission lines?
Limits of increasing يعني transmission lines?
Yeah.
Cost. The cost is the limit.
Oh, the only one is the cost.
Yeah. Because if you increase, it will increase the reliability and the stability. The other issue or the opposite direction or limitation is only the cost, because extra transmission lines means extra cost and extra maintenance and so on. Okay? يعني you have capital cost and running cost for any operating systems. تمام? So the limitation will be in terms of cost and maintenance. Any questions, شباب?
I don't know, but I think usually they use 2 transmission line or 2 branches, not increase it over that. Am I right, Doctor?
والله I'm not sure. يعني because I saw before many, not only 2. Where is the? يعني did you see this in any power plant?
Yeah, I sometimes actually they are going through this for many reasons, but the main reason is the costs. Sometimes we use 2 cables, 2 branches, maybe it will be less than using 1 cable due to costs. Mainly this process coming due to cost and reliability.
Yeah, but I mean, did you see 3, 4 or not?
No, actually in our plant I didn't see, just 2. I saw 2 transmission line there.
لا, but يعني theoretically it's possible to add it to N. Economically يعني it may be something else يعني according to any design. طبعا يا شباب يعني each power plant has its own design. يعني can find many designs for power plants. Okay, according to many aspects. يعني here we consider the stability. We can consider reliability also. يعني I'm not sure if there is a course here in the department called power system reliability or not. However, reliability, we have many systems. We have system called 100% continuity. For the 100% continuity systems, you have lots of varieties in order to operate the systems. يعني instead of having one supply for a system, if you have only one supply for a system, this system is called unreliable. However, if you have another source as standby, and if the first source fails to work, the second source will supply. This is called a reliable system. However, if you have many sources in parallel to support the failure of any primary sources, This is called 100% continuity. It's applied for the very critical loads, تمام? Like something like airports, okay? Like power plants, like water power plants as well, and so on. Okay. طب now يا شباب, how we can control the field in order to keep the power constant? Now we have a certain load. This load is constant, but let me give you an example first. We have a power plant, and the control center asked the power plant to increase its load, for instance, from 100 megavolt ampere to 150. So the new operating point now will be 150 megavolt ampere. So it was, firstly, it was 100 megavolt ampere, and it's required to be increased to 150 megavolt ampere. So the new operating point should fulfill the 150 megavolt ampere, which means if you increase the load on the generator from 100 to 150 at the same excitation voltage, the power angle will be increased. صح ولا غلط يا شباب؟ يعني we agreed on the figure we already made here in Word. Here, due to load increase, delta will be increased. صح ولا غلط؟
Yes.
صح.
So what will happen if delta increased without changing the excitation voltage? Power will be increased.
Yeah.
The power will be increased. Is it right? So here, if we increase the power needed from the machine to 150 megavolt ampere, so we expect to have increase in delta. How we can decrease delta? By increasing excitation. For that, we will see together here the effect of increasing or changing excitation at constant power. Constant power mean here or refer here to the second value here, which is 150 after the required value asked from the control center. So let's see, Shabab, here. This is an example. For instance, at case of IA3, here, and let's start from 3 to 1 to see what is the effect of increasing excitation on the power angle. Here, ya shabab, this is EF3, and this angle is delta 3. Okay, this is the angle of delta in case of 3. If we would like to increase the excitation, now for this case, the power factor was leading like that. If we increase the excitation a bit to reach to normal excitations at EF2, where the current is in phase with voltage. As you can see, this is called normal excitation at unity power factor. So this is here the angle of delta 2 from that line to this reference line. This is delta 2 now. So by increasing excitation from EF3 to EF2, the power angle decreased. So again, if we increase the excitation more, what will happen? Let's see, in case of EF1, you will find that at EF1, the current is lagging now. So we can change the power angle or decrease the power angle by increasing excitation. This is very important to be understood. And this is what happened in power plants when we need to increase the load. So this is an example. If we increase the load from 100 mega to 150, for instance, we need to increase the excitation. And this is an example. When we increase the excitation, the power angle will be decreased again. Why we need to decrease the power angle, Shabab?
To make the system stable.
Exactly, to avoid the operation at the unstable region or to avoid the unsynchronism, تمام, or loss of synchronism. This is the right answer. Fine. We can see this phasor diagram from another aspect. Mathematically, يا شباب, if we have a look to this length now, or this length here, it's equal to PE XS over VT. If you get it from the equation, you can find that the power equal EF V terminal over XS sine delta. صح ولا غلط؟ So B multiplied by X over V is nothing but EF sine delta. صح ولا غلط يا شباب؟ So this length means EF sine delta. If you have a look to the three vectors of EF, you will find that EF sine delta is equal for all of them. Is it right? صح يا شباب؟ EF1 sine delta 1 will give you this length. It's the same as EF2 sine delta 2, similar to EF3 sine delta 3. صح ولا غلط؟
Yes, yes.
جميل. طيب, regarding this length يا شباب, we assume that V terminal is constant. This is the terminal voltage of the generator or the grid voltage, which should be constant all of time. And assuming XS also, it's constant. This is the synchronous reactance of the machine. So this length now representing a constant power. So we can say now this line here, this line representing a locus for excitation voltage, EF or generated voltage at constant power. So this line again is locus for EF at constant power. Okay, شباب؟ طيب. Another line which is here, this length. If you have a look, this is the current IA, and this is the phi or angle of power factor. So we can say IA cosine phi equal this length, this segment length. Is it right? IA1 cosine phi 1 will be this A length. The same is also for IA2 cosine phi 2 and IA3 cosine phi 3. So we can say also this line representing the power, the constant power. Why? Because IA cosine phi, if we get the power equation from the general equation of power, you know power equal VI cosine phi. So if I cosine phi is constant, this means P over V is constant, and V is constant all of time. So this is also representing constant power line. So this is here, this line represents locus of armature current at V constant. From the comparison of the three relations, شباب, at lagging, leading, and unity power factor, we can say that IA1 cosine phi 1 equals IA2 cosine phi 2 equals IA3 cosine phi 3, and so on. And the same also for this line. We can say EF1 sine delta 1 equals EF2 sine delta 2 equals EF3 sine delta 3, and so on. So here, from this phasor diagram, it's very important in solving the problems. All of time, if we have constant power and we need to change the excitation or change the current or power factor, we can use these relations. Okay, شباب? Is it clear? طبعا here يعني you can have some questions. يعني what are the conditions of constant power operation of synchronous generator? These are the conditions. Drawing synchronous generator phasor diagram for constant power operation, showing the loci is the plural of locus. loci of armature current and generated voltage at different power factor conditions. So the solution is to write the equations and also drawing the phasor diagram. The same is also for synchronous motor, not only for generator. And this is for generator, and we have another curve for motor just by doing the same here for A for motor. Okay. Another effect is the effect of load changing under constant excitation. This is the first one which we said, but unfortunately the time is due now, the end of the class. So we will stop at that point, inshallah, and we can continue by the next class. Any question, Shabab? Any question?
Thank you.
Okay, Shabab. نراكم الكلاس القادم إن شاء الله. يلا في رعاية الله.
مع السلامة.
السلام عليكم.